So just to review, what has happened so far this week? Basically, we first met some of the key concepts about thermodynamics in an expanding universe. And then in the last lecture, we sort of very briefly met the two key applications, or two of the key applications of important thermodynamic events in the universe that you can sort of calculate the properties of more or less on the back of an envelope. And these are the thermodynamic events that we really understand. We predict things about them based on these thermodynamic arguments. We go out and measure, and the measurements agree with the predictions very well. And so now the idea is to get on to see to what extent the same thermodynamic principles give us hints about the various unexplained features of our universe, including the existence of dark matter, apparently. That'll be the subject of today's lecture, and the matter-antimatter asymmetry, which I'll talk about tomorrow, along with dark energy. So more generally, the basic idea. So this lecture, when we apply in the previous lecture, and in the tutorial on Tuesday, and in this lecture, there are these basic arguments, these basic thermodynamic arguments about that. They're kind of gross. Like I think I disliked them when I first met them in a cosmology course. And I imagine that many of you dislike them also. They're sort of not elegant. They're just sort of simple algebra, and then you have to plug in some numbers, and it's sort of gross. I don't like that sort of thing. I think Perimeter attracts people who don't like that sort of thing. But I just want to say, this is like, it's once you get the hang of it, it's just an extremely quick and powerful way to sort through fundamental theories for whether they are relevant or not to our cosmos. In other words, a very basic task. You have some new model of beyond the standard model physics. Does it have any hope of agreeing with cosmology, with cosmological observations? Well, roughly speaking, what you want to do is you want to imagine, okay, as the universe expanded and the temperature dropped, there are various massive particles in this new theory of yours. And as the temperature dropped past the mass of each of those particles, something interesting happened. And so if you sort of go through and pick out which of those particles are, probably as the universe went past each of those mass scales, it's quite likely that those particles annihilated or fell out of thermal equilibrium, did something interesting. Some relevant process suddenly dropped below the Hubble expansion rate at that time. And an interesting thing happened. If the universe was purely in equilibrium the whole time, there would be no interesting structure around today. You just have to as you go through these mass scales, determine what happened, what exactly fell out of equilibrium, or what annihilation process took place. Did you end up with a stable relic, a particle that was going to just sit around and live for the rest of cosmological history, in which your job is then to check, okay, well, now if that particle fell out of equilibrium at that point, and since then has just sat around and diluted with the expansion of the universe, is it 10 billion times bigger than the observed dark matter density today, in which case your model is toast? Is it 10 billion times smaller than the dark matter density today, in which case you don't need to worry about it? Basic questions like this. Or is it on the order of the dark matter density today, in which case your model is suddenly the leading contender for beyond the standard model physics? So this ability to quickly sort through a theory on the back of the envelope and just see whether, as the universe cooled, did it produce things that were vastly out of kilter with observations, or totally irrelevant, or right on the money for matching some currently unexplained phenomenon. Yeah, so that's really worth learning how to do, even though it's not the most elegant thing we'll do in this course. We'll get back to the more formally elegant stuff next week, all of next week. But for the next two lectures and for this previous one on CMB and BBN, we just want to get acquainted with this other style of thinking and see what it tells us. So, okay. By way of introduction, I think I've already said this, but fortunately or unfortunately, cosmology has for the past 15 years been in the same situation that the standard model of particle physics. There's now a so-called standard model of cosmology, just like there is a standard model of particle physics. And the situation is very similar, that ever since the late 70s or the mid 70s, we had the standard model of particle physics, and try as we may, every experiment we do seems to agree with the predictions of this model, which is great, except that this model has all sorts of puzzling things about it that we would like to understand, and experiments are giving us no new clues. We're kind of barren in terms of new evidence, new unexplained phenomena that don't fit the model. And cosmology is the same thing. Ever since about the late 90s or early 2000s, there was this model, the lambda. It became clear that this model, the lambda cold dark matter model, fit the data well, and together with a scale invariant spectrum of primordial perturbations, which we will talk about next week. Okay, so if you saw Kendrick's talk, this is ultimately a model with really 6 free parameters, but with it you just like this is a model with only 20-something free parameters, well, depending on how you count, but with it you can fit millions of observations. This guy has 6 free parameters, and with it you can also fit a gigantic amount of data at this point. And the impressiveness of that fit just continues to build. On the other hand, there's been basically no qualitatively new information about what the dark matter is, what the dark energy is in that time period. It's just that observations of the gravitational dynamics of the universe have converged more and more around this picture being correct. And okay, so the question is how to make further progress. So let's talk about dark matter in this lecture. So I just want to quickly give a whirlwind tour of kind of what is the observational reason to think there's dark matter out there. So why do most cosmologists believe in dark matter? How have we come to this embarrassing junction? Then there's a question of what's going on. So there's some phenomenon out there that's not explained by general relativity and the standard model of particle physics. Many different lines of evidence point to it at this point. So that's the first thing. I just want to give you a quick sort of overview of what those lines of evidence are. But then the question is, what's going on? Is general relativity right? In which case, there's some new unaccounted for stuff out there. Is that stuff atoms of the periodic table, ordinary matter, but just somehow hidden in some form that where we can't see it, maybe tied up in black holes? Is it some entirely new type of matter, maybe a new particle? So that's what that normally goes under the name dark matter. Or since try as we may, we continue to only really have evidence of this through its gravitational effects. The natural question is general relativity wrong? Is our theory of gravity wrong? And what we really are talking about here is modified gravity. So or something else. If you think I'm leaving something off the list, then I'd be happy to hear about it. But so by far, the dominant view in cosmology is that the correct answer is this, and so I'll try to explain why that is. Now, I have to say that I will slightly push at the end of this lecture the eccentric position that it could be this. So I think there was basically a big breakthrough a couple of years ago in 2011 that I'll just tell you briefly about. That roughly speaking, before then, there was no very satisfactory alternative to general relativity. Nothing that seemed good. Nothing that seemed. Everything. All proposed modified gravities looked much grosser than general relativity on theoretical grounds, and were theoretically inconsistent with themselves. Anyway, so there's really been a beautiful new theory of gravity that's been found, and we're still really in the process of working out what its consequences are. So it's not yet at the point, and maybe it never will get to the point where this actually accounts for the data like this does. I mean, this thing, you got to hand it to it. It accounts for a lot of data at this point. This guy, I just think there's a lot of potential. It's one of the most interesting things that's been going on recently in fundamental physics, in my view. So I just want to tell you a little bit about that. In my opinion, the jury is still out. I think even in this field, most people think of this as a possible alternative explanation for the dark energy, for the cosmological constant problem. But until you understand the theory, why rule out the other? I still think there's very much an interesting question of whether this can replace this. Okay. So what is the evidence for dark matter? You know, the classical evidence was the discovery was in the 1930s. This sort of famously irascible Swiss cosmologist, Fritz Zwicky, couldn't get along with anybody, but discovered a lot of good stuff. So what did he do? He was an optical astronomer. He observed that if you look at the sky, in certain places on the sky, you see, 100 or even 1,000 galaxies grouped right together on the sky, much more closely than the random distribution would suggest. So this is called a cluster of galaxies, and he understood that this was really a bound object. This is really these galaxies are all gravitationally bound together into some bigger object. That's called a cluster of galaxies. If you look at the redshifts of all of these galaxies, so if you basically measure how far away they are, how redshifted are all of their spectra, you confirm the fact that not only are they all at the same position on the sky, they're all basically the same distance away from you in space. So they're really some lump of galaxies over there. But the redshifts are not all quite the same. The redshifts are all slightly different, which indicates that these galaxies are whirling around one another. And basically, by measuring how different, what is the variance in their redshifts, you're basically measuring that's coming from the Doppler effect. You're measuring the variance in their line of sight velocities. So you're measuring, that's all you can do in cosmology. You can only measure the velocity in this component in the radial direction usually. But nevertheless, from that, you can get a picture of how fast the galaxies are moving around. And what he noticed is that, so we have this idea from Newtonian physics that for circular motion, the gravitational force should be balanced by those are two different letters. That says mv squared over r. Or so, in other words, if you have a cluster where its total mass is this, you get an estimate for what, if you know its mass and you know its size, if you know the sort of typical size of the object, r, and these guys are whirling around. Okay, this is strictly speaking for circular orbits, but really this is secretly also, you may have met the virial theorem. The virial theorem is supposed to be for a random set of self-gravitating particles. Gives the same answer. The point is that if you measure the size of the object and the velocity at which things are whirling around within it, according to Newton's law, you've measured the mass of the object. so you know he gets an estimate for the mass that way. So let's call that M1. And then instead he looks at how much light he can measure how far away the object is, and then how much light he's collecting, and so he can measure how intrinsically luminous these galaxies are. In other words, how many stars. He can basically estimate how many stars are there contained in all of these galaxies in order to emit all of the light that he's seeing from them. And he adds up the mass of all of those stars, and he gets another mass M2. And he found that this guy is more than 10 times bigger than this guy. So even with his crude, even at the crude level that he was able to estimate these two things back in the day, it was clear that they were inconsistent with one another. And so, okay, so that was the first observation that led someone to say maybe there's some extra dark matter out there. Now at that point, you might easily say, well, but okay, maybe that extra dark matter is just maybe it's just ordinary atoms floating around in here, gravitating, but just not clumped up into bright stars so that you can see them. Maybe dark matter is just ordinary matter, just dark, as the name suggests. Okay, so then there was a similar. For whatever reason.
Wait, a question about that.
Yeah.
Don't we know the distance by the intrinsic luminosity and the redshift? So what's the extra parameter in this measurement? Like, I guess
let's see. So we know Hubble's law, and so for nearby objects, if you measure their redshift, that tells you their distance. Hubble had already measured Hubble's constant. In the late 20s, and these things were going on, these observations were going on in the mid-30s. So in other words, he goes out and measures the redshift. He gets an estimate for the distance. Then he measures the apparent luminosity. If he knows the distance and the observed luminosity, he can figure out what the intrinsic luminosity is. Like if you measure how bright a light bulb is, and you know how far away it is, you know how actually intrinsically luminous it is. And then he says, okay. So if these are all stars, I can convert from how luminous they are to how massive they are. And again, there's some fudging at each step, but that's the basic logic. And so that's how, yeah.
But when you want to use Hubble's law, that's not applicable for the particular velocity. That's what we want, no? So
yeah, that's right. You use Hubble's law only to get the total distance from you. So there's an average redshift of all these galaxies. The average redshift is the thing that tells you how far away that cluster of galaxies is. Then there's the tiny fluctuations in the redshift around the mean value. That's what tells you how fast the galaxies are whirling around in the galaxy itself. I know you guys all think I'm pulling the wool over your eyes somewhere here, but it's legit. It's legit. It's a real inference. Okay, and then famously, so that was Wiki in the 30s. That historically didn't attract that much attention, to be honest. But then what attracted a lot of attention were Vera Rubin's observations of galaxies in the 70s. And so there, basically you see, so if about a third of galaxies are spirals. They have these. They have kind of a bulge in the center, and then they have this disk of guys. And in the disk, these particles are really moving on essentially circular. These stars, I should say, are moving on essentially circular orbits around the center. And you can just look out at a galaxy and measure. So when you look at one of these things, there's a bright bulge in the middle, and then there's arms that taper off at some finite distance. And beyond some distance from the middle of the galaxy. Which might be, like in the spiral in our galaxy in the Milky Way, this is about 10 kiloparsec. Oh, sorry, this is about 30 light years. See, I'm infected by astronomy lingo. All cosmologists are infected by astronomy lingo that bears no relation to rational units. But so this is something like tens of thousands of light years. Anyway, so what Vera Rubin does, but then you can just see. There's a few straggling stars out here, much smaller numbers. So they contribute essentially nothing to the light, but there's a few things you can see further out, also moving circularly. And so she measures again using the Doppler effect, using the redshifts on one side of the galaxy and the other, what is the rotation velocity along the line of sight to the galaxy as a function of the distance from the origin? Okay, so here we're plotting how fast are the stars whirling around the galaxy as a function of how far radially out are we looking. And the point is that if you so let's say if you plot where the light is here, the light might go up to about here. Okay, so this might be the radius of the visible light coming from the Milky Way galaxy. Well, of course, we don't actually measure this for the Milky Way because we're in the Milky Way. But for some spiral galaxy, the light ends here. So this is the light radius. And outside, once you get, if light was really equated with matter, if really all of the matter was bound up into the stars that were doing the emitting here, then Newton's law again would predict that the velocity should fall off as 1 over r to the half as you go out further. Just again applying this rule. Once roughly speaking, you're far enough away to a first approximation, all this mass looks like a point mass, and you can basically apply this rule, and the velocity should fall off in a certain way. And instead, what you see in galaxy after galaxy is that the velocity plateaus as you go out. Okay, so something is making the stars. Something is pulling on the stars harder than this naive application of Newton's law would suggest, making them accelerate more quickly. Okay, and again, so it became clear with this observation that there was more stuff out there, and you began to be able to quantitatively measure exactly how much more was out there than the visible light from the galaxies. Again, you could object that this is the same objection would apply here, that maybe it's just ordinary atoms that are just floating around as a dilute gas, or maybe they're tied up into black holes or just objects that just don't shine, and they're accounting for the mass. But it's sort of nothing that a fundamental physicist should get particularly worked up about. So let's see. Maybe now could I have the lights down? Thanks. Yeah. So and then there's this more modern observation that also gives you another way to see the same thing. So basically, this is a famous cluster observed by the Hubble Space Telescope, and if you measure, so you see all of these. So if you look at the galaxies here, there's some subset of the galaxies that all have the same redshift. They're really the galaxies in this cluster. The rest of these guys are galaxies behind the cluster, further away, that just happen to lie right behind the cluster as we look up to it. And those guys, some of them are, as their light passes through the galaxy, it's being stretched out and split into multiple images. Because by Einstein's theory, as the light passes through this strongly gravitating cluster, it gets bent, and so just like a converging lens will, stretch out certain appropriately placed images, or even split the images if the lens is sufficiently strangely shaped. You get these, you see tons of these so-called arcs. The sky and these things, and all of those arcs are, not really what the shapes of those galaxies. That the galaxies have been heavily distorted by the lensing of the intervening cluster. And it turns out that if general relativity is correct, you can work backwards from the shape of these various arcs to what the shape of the actual mass is of this cluster. what it actually needs to be to produce that lensing. And you find that, first of all, it's dramatically larger than the mass of all the stars you see here, of all the stars and all the galaxies that you see there. But first of all, also it extends to a much larger radius. It's at least a factor of 10 bigger than the in sort of radial scale than the size of the observed cluster itself. And so, but still, even if you acknowledge that there's tons of dark matter in the potentially boring sense, that there's just a lot of matter in all of these objects that we just don't see for some reason with astronomical telescopes, you could still perfectly well object to all of these lines of evidence that it could just be ordinary matter. So, but then nowadays we have more, let's say, modern lines of evidence that the problem is they all seem to point to the same abundance of dark matter as those classic galaxy and cluster lines of evidence, but they are not subject to this caveat that anyone has figured out a good way to explain them just using ordinary matter. In fact, before I talk about the cosmic microwave background, let's talk about the Big Bang nucleosynthesis, which we talked about yesterday. So yes, sorry, could I have the lights back, please? So yesterday, I explained how at some moment, when the temperature of the universe was about 1 mega electron volt, there was this transition that happened where all of the neutrons and protons in the universe, which previously had been separate particles, bound together to form the light elements in the periodic table. And in particular, we did a back-of-the-envelope calculation to show that when this happens, you get a split of the universe into about 75% hydrogen by mass and 25% helium by mass. And it turns out that estimate is rather robust. It doesn't really depend on this quantity eta, the so-called baryon to photon ratio, the number of baryons, the number of neutrons plus protons, or in other words, baryons that there were in the universe per photon at this time. But this same process explains a bunch of the other light elements and isotopes in the periodic table. And some of those explanations depend sensitively on this number. So in particular, the guy that depends most sensitively is deuterium. So that's the heavy isotope of hydrogen, which has 1 proton and 1 neutron in its nucleus. So there is some cosmic observed abundance of deuterium out there. And also our explanation for that is that it came from the Big Bang. Now there, it turns out that as you vary the fraction of photons to baryons at that time, you vary the predicted amount of deuterium a lot. And so by looking out at the actual observed cosmic abundance of deuterium, you get a measurement of this guy. And again, the exact value is not crucial here, but the main point that I want to say is that, so this is the number of photons per baryons, nucleons, neutrons plus protons. And that's the same as it is today. That value was conserved between that moment and the present. So now you can look out today. Well, we measure how many photons there are in the universe. When you measure the cosmic microwave background and you measure its temperature, that immediately turns into that, if you measure a Planck spectrum and you measure its temperature, you have measured the number of photons per unit volume. And we also have a measurement of the number of neutrons and protons per unit volume. And that measurement today agrees with, it basically agrees to within a factor of 2 with the ratio that you get by saying that the baryons in the universe are the light that you see in galaxies and clusters. It disagrees by a large factor with the ratio you would get if you said all of this extra mass in these galaxies and clusters was just more neutrons and protons, more baryons, but just hidden from us. Okay, so is that clear? So so we do some measurement of nuclear physics in the early universe, and we get a predicted number of photons per baryons today. And that predicted number is inconsistent by a factor of 5 with the value you would need if you wanted to say that all of the observed dark matter in these clusters, and if you wanted to explain the fact that everywhere you seem to look in the universe today, there appears to be about 5 times more gravitating mass than the amount of actually atoms you can lay eyes on one way or another. Yeah.
Are there any theories in which eta has changed since the Big Bang value?
It's very hard to do that since the okay. That's a good segue to the next thing I wanted to say, which is that so the cosmic microwave background now gives us an independent. So that was 1 second after the Big Bang. This was a few 100,000 years after the Big Bang. So it turns out you get another measurement. You get an independent measurement of this quantity eta here, which is more accurate, and also everyone regards it as more reliable, basically. But it agrees with the one from Big Bang nucleosynthesis. So that is not only one of our key cross checks that we really understand what's going on both in the CMB and the much earlier Big Bang nucleosynthesis process, but it also solidifies this argument. So most people today would say that the most rock solid argument for non-baryonic dark matter is that. Let me just say physically why it is. So I want to say that you know, we think we understand that we have this predicted curve that exquisitely fits the observed data by the Planck satellite. Okay, and there is a particular physical mechanism that goes into predicting the shape of this curve, and the fact that it fits so well makes us very confident that we understand the basic physics here correctly. And the basic physics, dark matter just plays a fundamental role in the whole reason there's bumps and wiggles here. And if you try to fit this data in the absence of dark matter, it's ruled out at this point at something like 30 sigma or something like very, very, extraordinarily high significance. Okay, so in short, just briefly, what is the physics? So at this time when the cosmic microwave background photons were released, so again, remember this is they come to us from the moment when electrons and protons decided it was finally worth their while to bind together into atoms, when the universe cooled down enough that neutral atoms formed. So now think about the universe just before that. It has in the presence of dark matter, it has 2 key components. Okay, there is on the one hand a plasma consisting of all of the photons that are rattling around and the electrons that they're bouncing off of and the protons that they're bouncing off of. Okay, and these guys love to bounce off of one another so much, and they were so dense at that time that they formed this. They were very tightly coupled together. This tightly coupled together soup. No, you can't. In this, if you took a tweezers and grabbed an electron and tried to drag it this way, you would drag all of its neighboring photons and electrons with it. They're all really tightly coupled together. So think of that as one component. And then there's dark matter, who doesn't talk to anybody, total loner. So the idea is that this thing has a lot of pressure, and so if there's a little region in the universe, suppose there's a little region in the universe where instead of the energy density being completely uniform, independent of position in space, it's oscillating a little bit. So there's some regions that are a little bit more dense than the cosmic mean, some regions that are a little bit less dense. And okay, but we have these two components, so at early times, there's the dark matter, which is, let's say, the white curve, which is a little bit more dense here, and then then there's this plasma, which is more dense. Now, it turns out that ever since the beginning of matter domination, ever since the matter became more important, the non-relativistic matter became more important than radiation, this guy began to grow. So regions that had a little bit more dark matter, they also had a little bit stronger gravitational pull in these regions. They began to pull dark matter in from the surrounding low-density regions, and so the overdensity here increased with time and increased. Meanwhile, the green guy behaves different, this plasma, because it's still the case that the region that has this region here, because it has more plasma and more dark matter, it has a stronger gravitational, it has a deeper gravitational potential than its surrounding area. So matter wants to, so the plasma also gravitationally wants to fall into that well, but it also is full of photons. It's tightly coupled to relativistic particles, which don't like to be pulled around by gravity. They like to do their own thing. They have a huge pressure. They have a huge relativistic pressure that wants to blow any dense region apart. Photons like to iron themselves out and be completely, statistically, they like to be uniform. And so what happens is that there's a competition, and the two sides oscillate back and forth. And what's going on is there's a sound wave here. So first, the plasma tries to fall in a little bit, and gravity wins, but it's greedy. It overdoes it, gets a little bit too dense, and the photons are like, I'm finished with this. Get me out of here. And they begin to scatter away, and so then the density decreases, and it does this business where it oscillates. Where it oscillates up and down in its potential wells. And so if you think of this on different scales, so here I've just plotted one particular wavelength, one particular Fourier mode of the density field, and discussed how it would oscillate. But now if I looked at a different Fourier mode, if I thought about a Fourier mode that had a much shorter wavelength, sorry, making a mess here, but hopefully you get the picture. There's another, if I focus instead, if I use my Fourier glasses and focus on a different, shorter wavelength of the universe, the physics is exactly the same. It does this business where the dark matter potentials grow, the plasma oscillates like a sound wave inside those potentials. It just does it all faster. Okay, the speed of sound is the same, so if the wavelength is smaller, the frequency is proportionally higher. So, what you're looking at here is the various peaks correspond to the particular wavelengths in the universe that had the good fortune, or for which it happened to be the case, that as they were oscillating, right at the moment where they reached their peak of oscillation amplitude, so that right at the moment where the plasma reached its peak of oscillation amplitude, the universe became neutral, and all of the photons were emitted. Okay, so the first peak here is the longest, is the wavelength that was so long that from the time of the Big Bang, or the time of the beginning of the matter-dominated era, until the moment when the CMB was released, it had time to oscillate exactly, half an oscillation, basically. It had time to go from its initial state up to its first peak one time. Then there's a shorter mode that oscillates a little bit faster, and between the Big Bang and the time of the time that the CMB was released, it had time to oscillate up and then oscillate. Sorry, I should be using the green. It had time to oscillate to a maximum and then oscillate back down to a minimum, back to an anti-maximum, let's say. So that's the second peak, and then there's a third peak that had time to oscillate up and then down and then back up to its maximum. So when it underwent 3/2 of an oscillation before the CMB was released. Okay, so I just explained that. Well, first of all, that's a thing that you should at least have a cartoon picture of at the end of any good cosmology course at this point. But so the point is that dark matter played a critical role here in terms of setting the in terms of basically providing deep potential wells that kept this thing that set the size and frequency of these oscillations. And as I say, if you just work through in detail and try to account for the same spectrum without dark matter, just using this photon baryon plasma and trying to tune, as you will, the amount of the density of protons relative to photons, you cannot do it. Okay. So instead, you get a direct measurement for when you fit this data, you get a measurement for how much dark matter there was in the universe, how much baryons, in other words, how much protons here, and how much photons. And again, the baryon to photon ratio agrees with the BBN estimate, and the baryon to dark matter ratio agrees with all these other observations, which measure that there's about 5 times as much dark matter everywhere as there is baryons. Yeah.
So this baryon fluctuation, the CMB map is a result of this fluctuation?
Yeah, basically that's right. If you happen to be talking about a mode that reached its maximum, that reached its maximum here right at the moment that the CMB was released. This is an extremely messy figure at this point. Kind of doesn't make sense for me to keep pointing at this, but okay. So this, so imagine you're looking up with your telescope. If you look at that point on the sky, you see a hot spot because it's a dense region. Whereas as the plasma crushed together here, it got very hot. It got very hot, and so its pressure is about to drive it out. But you took a picture of it right when it was at its point of being maximally heated up. And then there's if you follow the same mode to where its minimum was, you see a cold spot on the CMB over there. All of the hot and cold spots on the CMB are exactly that. Exactly. That's right. Exactly. Yeah. Okay. I think I'm just going to leave. There are a few other. There are, by this point, really a variety of lines of evidence. Yeah.
Why? I mean, it looks like very convenient that the error bars in the part that doesn't match are bigger than the rest.
Yeah, that's true. That it's the they match. They match. I mean, as the error bars get bigger, if the error bars are correctly sized, you should see the points always deviating more and more from the curve because they should always be deviating on average by about 1 error bar. So if the error bars get bigger, it's not surprising that the points also lie further off the curve. So these error bars come from something called cosmic variance. They come from the fact that they come from the fact that remember I said how you measure. So the cosmic microwave background is consistent. We did this decomposition. We said that temperature is a function of angle on the sky. Is consistent if we decompose it into spherical harmonics, L and M. So we have coefficients times the various spherical harmonic functions on the sky. So at a given value, these ALMs that we measure when we make a map of the cosmic microwave background, they appear to be consistent with the statement that they were each randomly drawn from a probability distribution with whose variance is given by the following expression. There's some variance that only depends on the quantum number L, and then otherwise these things are uncorrelated with one another. For different values of L and M, they're uncorrelated. So there's a delta function in L, and there's a delta function in M. So in other words, you draw one of these ALMs, and regardless of what value you get for it, it doesn't affect what you should expect for the other values of ALM that you draw. They only depend on this quantity C sub L. And so now this is the thing we're trying to measure and plot here. And so how do we measure it? This is the parameter in a statistical distribution. Unfortunately, our universe only represents one draw from that statistical distribution. So we don't get to run the universe again and again like we would an experiment. So the best we can do to measure C sub L, to estimate C sub L, is to take, since it only depends on L, that means that for every value of M at that L, we've taken an independent measurement of this guy. And so we just average those measurements. We say the variance, our estimate for the variance is, but we just sum up over all of the ALMs we measure their absolute values squared, and we just take the average of that to get the estimated variance. There's 2L plus 1 of them. So that's how we measure. That's how we actually estimate. We make a map, we Fourier decompose it, and that's how we actually estimate each of these points. But these error bars then are coming from the fact that we've, instead of estimating the statistical quantity by taking an infinite number of draws from our statistical distribution and calculating the variance, we've only, at each value of M, we've only been allowed a finite number of draws, namely 2L plus 1. Well, at high L, if you're up at L of 1,000, that's not so bad. That means you got to take 2,000 draws and average that. So that you're going to get quite good statistics. You're going to get a quite good statistical measurement of the variance, which is why you have tiny error bars up here. But down here, at L equals 2, you only measure 5 different ALMs with L equals 2. And so you're calculating the variance of a distribution based on only 5 draws from that distribution. And so the statistical uncertainty in your measurement of the variance is going to be very large intrinsically. And that's this phenomenon called cosmic variance, that this seemingly inescapable fact that we're trying to measure the shape of a statistical distribution, but at low L's we only get to take very few draws, random draws from that statistical distribution. And we have to just do the best we can based on that few number of those few draws to infer its shape. But statistically speaking, the points down here, so that's why they have bigger error bars and tend to lie further off of the predicted curve. But statistically, these guys down here are just as consistent as these guys up here. They're all well, depends on how you slice and dice the data. Some people say there's kind of 2 sigma-ish anomalies down here. But that's another story. I think those are all, probably you shouldn't pay too much attention to them because a 2 sigma anomaly in cosmology, it's like in particle physics, you're not allowed to claim detection of the Higgs boson until you've detected it with 5 sigma significance. Unfortunately, in cosmology, the culture is not so rigorous. If you see a 2 sigma or 3 sigma hint, you claim a detection of something, but then like 75% of the time, those detections turn out to go away with further data. Here, the problem is we'll never get further data. So they'll never have a chance to go away, but you probably should regard them with the same skepticism that you regard any other 2 sigma deviation in cosmology. Yeah?
What's the effect of nonlinearity in this Fourier decomposition? Isn't gravity famously nonlinear?
Yeah, that's a good question. So it's an observed fact about the Standard Model, about the early universe, that we get lucky in that regard, that everything in the early universe, the metric, the distribution of the dark matter, the distribution of the plasma, are all observed to be almost perfectly homogeneous, almost perfectly unperturbed. So fortunately, even though Einstein's equation is nonlinear, you can solve exactly for the unperturbed solution. That's the Friedmann equation, and you're solving the Friedmann equation. So to a zeroth order approximation, we can get the exact solution. And then the deviations from that are so tiny that we can linearize Einstein's equations. And because the perturbations are so tiny, that the quadratic corrections to that linearized approximation are negligibly small until late times. Today, the density in the universe really is fluctuates wildly. You know, you're a lot more dense than the air around you, and then that's a lot more dense than interstellar space. But that's one of the reasons that the CMB is so powerful. Is it's just all the physics can be linearized to outstandingly good approximation, and you can just solve everything without doing any monstrous numerical simulations or anything like that, and vary parameters at will and test them all against the data. So it's not like merging black holes. In other words, that's a problem where you really nonlinearities of Einstein's equations are really important, and you need it to simulate it numerically. Okay. Yikes. So I'm having too much fun describing the observational tests. Oh, now I did start late. How late did I start? I kind of want to not continue going over every day. But I started 10 minutes after. Is that right? Okay. Okay. Well, so that's the end of the summary of the evidence then. I don't know why I'm erasing that. Let me go over here. So the question is, what's going on? And so again, it looks like basically we can kind of split up. Let's try to sort of think systematically about what the possibilities are. The evidence that I have described so far, the way dark matter shows its face in all of these observations is through its gravitational attraction on other things. There's no evidence today of dark matter doing something else, of bumping into something directly that is interacting with it with a non-gravitational force, or emitting a particle that we can observe, despite a lot of effort for people to look for such things. So one possibility is GR is wrong. In other words, if GR is right, it appears that there's some extra unaccounted for stuff that's not the stuff in the periodic table. But we only see it gravitationally. Well, one possibility is our theory of gravity is wrong. And the other possibility is that there really is new stuff out there. So now the new stuff, again, it could be either atoms or, new physics. New physics in the matter sector. So this is sometimes divided into two names. Now, I've already said that it seems that atoms using ordinary atoms to explain dark matter isn't allowed. But you maybe could wiggle out of that. Really. So, for example, if I took all those atoms and somehow collapsed them into black holes primordially, somehow, if maybe the dark matter really is just atoms from the periodic table, but it's collapsed into black holes of some size prior to Big Bang nucleosynthesis. So that by the time Big Bang nucleosynthesis rolled around, even though all those baryons that were locked away in dark matter in black holes were irrelevant for the process of nucleosynthesis, and those guys. So in other words, one possibility, which could even involve dark matter actually being made of ordinary atoms, is the idea that when we see extra matter. There's a simpler way to say this. There's two possibilities here. One is that the dark matter is clumped into macroscopic stuff. So those are called, the acronym there is Massive Compact Halo Objects, or MACHOs. So in other words, maybe our galaxy is full of dark clumps of stuff. Maybe black holes. Maybe, I don't know. Maybe little things like Pluto. But macroscopic things that are flying around in the galaxy, and they just don't shine. And maybe, as I say, if you could manage to figure out how to form such things prior to Big Bang nucleosynthesis, maybe those could even be made of ordinary atoms. And then the other possibility is that they're elementary particles. It's just some new elementary particle that we haven't managed to lay our hands on non-gravitationally yet. Okay, and so those are called weakly interacting massive particles. So we have MACHOs and WIMPs, these cleverly chosen acronyms. So turns out this possibility is heavily constrained, although not completely ruled out. And so in short, there was a clever idea by this astronomer Bohdan Paczynski in the 80s. He pointed out that if, let's say, so if the dark matter in our own galaxy was really made of macroscopic, massive dark objects floating around, like black holes, then you would be able to see them by so-called gravitational microlensing. Okay, so in other words, the effect is gravitational lensing again, just like we saw in that previous image. It's the bending. Ultimately, the effect we're going to look for is due to gravitational bending of light rays by Einstein's theory of general relativity. But now the situation is you look at a star, and imagine a little dark thing the size of Jupiter that you can't see directly flies across the line of sight to that star. Then, okay, so now I'm the star, and David is observing me. And I'm emitting some rays directly towards him, but then I'm emitting some rays that go just over his head and just below his feet, so he doesn't observe them. But then Jupiter comes across my path, and its gravitational effect tilts those rays, so now David sees those too. So he sees a little bit more of the light from me. And so if you monitor the intensity of this star as a function of time, as Jupiter crosses in front of it, you'll see it. You'll see a little blip in it. Its intensity will rise and go back down with a certain predicted shape as a dark matter goes in front of it. And so, for most stars, you're not going to get lucky enough. If you just choose your favorite star, go out and look at it, and just sit around and wait until it goes up and down. Turns out you have to wait a long time. But but you can monitor, many millions of stars, so they monitor many millions of stars, and wait to see whether any of them undergoes a blip. And to make a long story short, they monitor them. They, roughly speaking, don't see any blips. The non-observation of blips basically rules out MACHOs in the range, in what most people would have regarded as the most interesting range. Okay, so it turns out those observations rule out MACHOs between 10 to the minus 8 times the mass of the sun, so that's about the mass of Pluto, up to 100 times the mass of the sun. So anyway, they're very. There's a little bit of astrophysical prejudice coming in here, but when people thought about this idea, they regarded this as the most plausible range, and that most plausible range has been ruled out. It seems rather unlikely that it could be bigger than this, that the MACHOs could be bigger than about 10 to the 2 solar masses without having other more direct gravitational effects, seeing some star whipping bound to this thing and whipping around it or something. On the other hand, it could still be the case that MACHOs are just smaller smaller than Pluto, basically. It turns out they can't be smaller than about 10 to the minus 19 times the mass of the sun, because then even if you kind of crush them into their most stable form as a black hole, that black hole will still Hawking evaporate in less than the age of the universe. But there's still this window. There's still the 10 orders of magnitude of window, where in principle, if you can somehow make these things, make these what by astrophysical standards ultra small objects out of the dark matter, it could still be that. So then, yeah, I just Okay, so then on the other hand, if it's WIMPs, now I really am just going to take. I beg to take just 5 more minutes because I want to go through enough of the next calculation that it'll be possible to do the tutorial. Yeah.
I just wanted a question. You say that the only possibilities are matrices and WIMPs, but aren't there also like axions and other new types of?
I'm including those all as WIMPs, and that's what I'm about to talk about.
Okay. Well,
I
thought there were other candidates that weren't weakly.
So I'm calling anything that yeah, if you mean weak.
But a WIMP was like a specific.
Okay, so let me get there. I'm using WIMP to mean, people mean slightly different things sometimes when they say it. I'm using WIMP to mean any elementary particle. It's just some elementary particle out there that's massive that we haven't detected except by its gravity. It's true, weak also sometimes refers to the weak force. And when people talk about a WIMP, they sometimes mean that by weak, not just that its interactions are extremely weak, but that they're actually the scale of the weak force, as if it was mediated by a W boson. That's not what I mean. But I'll talk about that'll be one of the subcategories. Okay, so in short, I'll leave a little discussion of massive gravity to the next, or modified gravity to the next one. But I just want to say, so if there are massive elementary particles out there that are really the dark matter, it's useful to break those up into 2 categories. Okay, so either at sufficiently early times when the universe was much more dense than it is today, these particles might have been in thermal equilibrium with the rest of the particles in the universe, so with the rest of the radiation density. And then as the universe cooled, they just at some point fell out of equilibrium and persisted, were just stable particles that no longer interacted with anything and persisted until the present day. But if that's the case, so you call those, that would be called a thermal relic. That's a very predictive scenario. If it was once upon a time in thermal equilibrium with the rest of the particles in the universe, and then its abundance today is ultimately set by the fact that at some moment in the early universe, it ceased to be able to, its interactions were no longer strong enough to keep it in thermal equilibrium with the rest of the matter. You tend to get quite sharp, relatively sharp predictions for today. The other possibility is that it's just something else. Maybe it was never in thermal equilibrium, and its abundance today is just set by some other physics. Okay, so there's a famous example. There's sort of the classic candidate for such a particle, which is the axion. There's a problem in the standard model, which I won't, because I'm running out of time, won't describe it. There's the so-called strong CP problem in the standard model. The axion was a new particle that was invented to explain that problem, but then people realized, oh, it also could be a good non-thermal dark matter candidate. You will meet this guy in more detail in the tutorial. If it's a thermal relic, then it's useful to further subdivide here. We split these guys into hot thermal relics and cold thermal relics. So what this means is that if at the moment that the particle dropped out of thermal equilibrium, it was still relativistic. Its energy was still well above its mass. The temperature was still well above its mass. That's a hot thermal relic. If it fell out of equilibrium when it was cold, when it was non-relativistic, we call that a cold thermal relic. Okay, so this guy, again, you will calculate its abundance in the tutorial, and it turns out what you'll see in that calculation is that it turns out that this guy, if the particles in the early universe were just if there was just some heavy particle chi in the early universe, and let's say that chi plus chi, or chi plus chi bar, a chi particle and its antiparticle can annihilate to some standard model particles. Let's say it's 2 photons. So in the early universe, these guys are happily maintaining their thermal abundance by just, they just create themselves and destroy themselves by this process until they have the abundance required by thermodynamics. But then suddenly, in the early universe, the temperature dropped below the mass of this chi particle, and thermodynamics started to kill these guys, started making it favorable, exponentially suppressed their abundance, made them want to annihilate to photons and all disappear. And so they disappeared and disappeared until they got very sparse. And at some point, they just got so sparse that, that this poor chi could no longer find a chi bar to annihilate with. And it was just out of luck. And so it just hung around for the rest of the history of the universe, lonely guy wandering around looking for a chi bar to annihilate without success. So it turns out that if that is what set the dark matter abundance, so in other words, if you have a cold relic, well, you can estimate how big does this cross section have to be in order that if you calculate the resulting abundance of this particle today, it matches the observed dark matter abundance. The answer is that this cross-section has to be roughly a weak scale cross-section in the sense of Kirin. It has to be roughly, it has to be something like 10 to the minus 10 GeV to the minus 2. Or in other words, this is of order the Fermi constant squared times m chi squared, if m chi is kind of a standard, ordinary physics scale, 1 GeV, the mass of the. So if the dark matter particle has the same mass as the proton and interacts weakly, it turns out that this annihilation process will give you, at the present day, a dark matter abundance that matches observations. Yeah.
Could we have a case similar to the baryons in which they don't completely annihilate, there's some asymmetry between the chi and chi bar?
Yes. So yeah. In fact, that is another. So this thing is the so-called WIMP miracle, and in this scenario where you sort of where the numbers turn out right to make the relevant cross section natural from a physics scale, in that scenario that's not what we're talking about. There are other interesting scenarios that have been proposed that try to sort of simultaneously explain, do something analogous to what you say. Because there's another puzzle in the universe, which is why is it that the dark matter abundance is so close to the baryon abundance? Why is it that they only differ by about a factor of 5 when they could, in principle, be totally unrelated things? And so people have models where something like exactly what you say happens, that there's total matter-antimatter equality, but that it's shifted so that there's a little bit of excess antimatter in the dark sector, a little bit of excess matter in the ordinary sector. And what happens is there's total annihilation, but with some leftover particles over here, some leftover antiparticles over here, and then these guys are the matter and these guys are the dark matter. So that's another interesting possibility. Okay, so that's the so-called WIMP miracle. Now, unfortunately, that suggests that WIMP miracle. The exciting thing was that it suggested that the cross section for these guys interacting with standard model particles was of order the weak scale. And that makes you think, oh, maybe I'll be able to go out and detect those, either indirectly in astrophysical observations, or directly if I go to a deep underground mine and have a huge vat of some pure sample and I just wait for dark matter particle to come and run into it. roughly speaking, if the cross-section is this big, if I make my vat big enough, I should begin to see some of these guys. And so that has motivated like 30 years of dark matter experiments of various sorts. And again, there's been no success in that direction. So there's kind of a point working in this guy's favor, which is that the scales turn out to be plausible from a particle physics standpoint. But on the other hand, the experiments that are motivated by that observation have turned up nothing. Nevertheless, this is somehow in everyone's mind still by far the what everyone thinks the dark matter is. Somehow everyone still thinks. And also, yeah. Anyway, so and it may be. I don't mean to say that the non-detection of experiments actually rules out this possibility. It doesn't. It's just that they've ruled out a lot of the parameter space, but not all of the parameter space. It's exactly like the situation with supersymmetry. You may have heard that LHC. Everyone thought it was. People thought they were going to detect SUSY. They didn't detect it. It's kind of a crushing blow for supersymmetry. On the other hand, does it actually a killer blow for supersymmetry? Does it actually formally rule out all of the parameter space? No, there's still plenty of parameter space. And so you have to judge for yourself what to make of that. But so the situation is analogous here. I just wanted to quickly say this dude is actually ruled out. A non-thermal relic, a thermal relic that was relativistic. And I just want to quickly, this is the simplest calculation to do. I want to sketch it so that you'll get the basic idea of how such calculations go and can do the subsequent two in the tutorial. I'll really just do this in 1 minute. Where should I do it exactly? Ooh. This is breaking new ground for me. Okay, so let's say, so a very standard sort of line of reasoning in cosmology is the following. You have some particle, it's in thermal equilibrium. Its abundance is happily going along, set by the thermal equilibrium abundance relevant to it at some temperature. But there's some reaction that's holding it in thermal equilibrium that has a rate gamma, which also depends on the temperature. And at some point, that rate drops below the Hubble rate, at which point this guy no longer maintains its thermal abundance. Thermal equilibrium no longer controls its abundance. Instead, if this is a stable particle, it no longer talks to the rest of the particles in the universe. It just hangs around. It just hangs around for the rest of eternity. So now, its physical abundance, so this is, let's call this moment T sub f, T freeze out. So at that moment, its physical abundance, its number per physical volume was n evaluated at this particular time or this particular temperature, T sub f. So let's call that n sub f. Then what happens to n as the universe subsequently expands? Well, the total number of these particles stays fixed. But so we have our universe here, and now let's look at the little box. And we have a bunch of n particles that have suddenly frozen out and are no longer talking to anyone else in the universe. And I've just arbitrarily drawn with a marker a little box on the balloon. And now as the universe expands, the volume of this three-dimensional box grows as a cubed. V is proportional to a cubed. And so the number of particles per volume, well, the number stays fixed because they're just stable particles that no longer are talking to anybody. They're just sitting there. But the volume goes as a cubed. So this thing goes like a to the minus 3. On the other hand, in these scenarios, we imagine that ever since the moment of decoupling here, ever since the moment of freeze out, the rest of the universe expanded adiabatically. There was, things happened. You were born, and various wars were fought. But in the whole process, the cosmic entropy budget was not significantly affected. So the total entropy within a given box also stayed constant. And so the entropy density, the entropy per volume, also scaled since that time as a to the minus 3. And so in particular, that means that the ratio of the number density of this relic particle over the total entropy density of the universe was a constant between the moment of freeze out and today. So this the ratio at the moment of freeze out was equal to the ratio today. Okay, the number density of that particle over the entropy density at the moment when it froze out is equal to the number density of that particle today over the entropy of the universe today. Now, okay, but the point is that we can use our thermodynamic formulae to calculate every term in this expression except for n0, and then get an expression for the number density today, the predicted number density today of these relics. In other words, we just rewrite this expression as n0 is equal to S0 times n sub f over S sub f. And we just calculate these three guys, calculate the number density today, and then if this is some massive particle, its energy density today is given by the mass of that particle, the mass of this particle, let's call it chi, times its number density today. And we just check. We do this calculation. We check, OK, is the predicted energy density today 10 times bigger than the critical density of the measured critical density of the universe today? Remember, there's this critical density. The difference between the universe being open and closed and or flat today is 3 times the measured Hubble constant over 8 pi times g Newton. So if we go through and we calculate this thing and it's 10 times bigger than this, no luck. That model is ruled out. If it's 10 times, if it's a billion times smaller than this, the model is not ruled out, but it's also not the dark matter, because the dark matter has a density today that's comparable to this. The dark matter today has a density that's about 25% of the critical density. On the other hand, if we do the calculation, we find out this thing is 25% of this, then we say, wait a minute, I might have just discovered the dark matter. Okay? So just can I abandon ship at this point and still have the tutorial be doable? What do you feel, David? You think yes? I want to go one line further. Yeah.
Doesn't that rho equals n0 only apply if m is cold?
Yes. Yeah. So the dark matter is observed to be a non-relativistic gas of particles. So this should be approximately correct. Okay. So let's just see how we would calculate this guy. Well, suppose it was relativistic when it froze out. Well, we know that we had derived in a previous lecture that the energy density of that the number density of a relativistic species was some order 1 factor times t cubed. So this is t freeze out cubed. And the entropy density was also that we found for a relativistic species. Meanwhile, the entropy density today is given by the entropy density in photons today is once again it's dominated by the cosmic microwave background, and so the entropy density is again that of a relativistic species. But now T0 here is the measured temperature of the cosmic microwave background, 3 Kelvin. Okay, so if you plug this expression, and this expression in, well, first of all, the T freeze-outs cancel, so it doesn't. So the answer is independent of T freeze-out, which is good because we don't know T freeze-out. So basically, this says that the number density of such particles today, roughly speaking, neglecting all these order 1 factors, it says the number density of the particles today, when you plug in these 3 expressions, is equal to the entropy density of the CMB today. It's basically equal to the temperature of the CMB to the 3rd power. And so now you can ask, well, if this particle is a massive particle that has the same entropy density as the CMB, but the temperature, but an unknown mass, how big can that mass be to not exceed the critical density? And if you just plug in numbers, you'll find that the mass has to be less than about 10 eV. That's very light. That's much lighter than any particle in the Standard Model except for the light neutrinos. Turns out that it's so light that this particle is ruled out as the dark matter. If it was this light, it would have not clumped into potential wells like it is supposed to form the observed structure in the universe. Anyway, this is not the time to tell you about that. I just wanted to say this trick gets used again and again. There's some event that sets its abundance, the freeze-out time or decoupling or some deviation from thermal equilibrium. And then you say this ratio, the number of the relic particle over the total entropy density, is conserved between then and today. Gives you a simple way to estimate the number density today and then convert that to an energy density and check, is it plausible or is it not plausible? Okay, so as I say, in the tutorial, you'll do a calculation very much analogous to that for the cold thermal relic, where you should get an answer that basically works, and for the non-thermal relic, axion-like relic, where you should again get an answer that can be made to work. Okay, I apologize for running over. I should have put the part that was essential for the tutorial at the beginning, but logically it didn't make sense. Anyway, I swear the next lecture is going to be. But also we skipped the last lecture, so this is like, no, you're not buying that argument. So anyway, I apologize. I know I keep apologizing. Next time I'm really going to be on time, and I guarantee that my average number of minutes in lecture will end up being less than Davide's.